Hi guys, it's Myla here. Welcome back to my channel. Today we're continuing with our SWK 210, which is strength of material. We're looking at chapter 1. Today we're looking at problem 1.5. Previously we looked at problem 1.1. So we have a figure here and also a problem statement that says a strain gouge located at C on the surface of the bone, this is C, indicates that the average normal stress in the bone is 3.80 megapascals when the bone is subjected to two 1200 forces as shown. Assuming the cross section of the bone at C to be annular and knowing that its outer diameter is 25 millimeters, determine the inner diameter of the bone's cross section at C. So basically here they are telling us that the bone is hollow, so it's annular. They are basically telling us that the bone is hollow and the outside diameter of the bone is 25 millimeters. Now they need the inside diameter of the bone. Can I just write across a little cross section here just to illustrate something? This is actually the bone at C. So I'm sorry for not. Yeah, this is it. So yeah. This is the bone and this is C. I just chopped it by half. So we have the outside diameter, which is, let me say, DO, and we have here the inside diameter, which is DI. So they are telling us that at C here, the outside diameter is 25 millimeters and the stress at this point is actually 3.8 megapascals. So what they want is the inside diameter. So looking at the problem, it's important if we were to if they want the inside diameter and we already have the outside diameter, if we were to find the cross-sectional area, which is this area here, if we were to find this area, we can simply use our normal mathematics, high school mathematics, to actually find our internal diameter. So the first approach to the problem is going to be to find the area of the cross section, and it's not difficult because remember we already have our stress at C, which is 3.85, and we also have these two forces here. So I'm just gonna use the general or the normal and known equations. So we just say the stress at C is equals to P all over the area at C. So yeah, we're actually focusing here. So with that said, I can just rearrange and say therefore the area at C is equals to P all over the stress at C. Well, this is simple arithmetic. So with that said, now if we know the P and the stress, we can calculate the area, and if we get the area, that area is actually the cross section here. And if we find that area, then we can actually be able to easily use our simple arithmetic to calculate the internal diameter. Now, with that said, we can actually just do substitutions. Now, a very important principle of this question or of this module is here. Now we have two forces of 1200 each. The question is, do we use 1200 newtons here for P, or do we use 2400 because there are two? Now the thing is, we're going to need to use 1200, but how? The answer to that is actually has a lot to do with Newton's third law, which is an action-reaction law, which says for every action there's an equal but opposite reaction. So I'll just make a simple illustration here just to remind you of our problem 1.1. Remember, problem 1.1 had something like this, where we had the first beam welded to the second beam, and they were mounted to a wall here. This was a wall here, right? And on this beam we had P, right? And here we had I think it was 1120 kilonewtons, something like that, yeah, and another one of 120 kilonewtons. Now this was stationary because it was mounted on a beam. So even if P was pulling it that side and causing some strain, some tensile strain into the two beams, it didn't move because it was mounted. And in the same way, the two forces which were compressing this beam, it was A, B, C. The two forces which were actually compressing rod BC towards the wall also were causing a compressive stress in B, or rather in rod BC. And with that said, when we did the calculations, we only considered P and the two forces. And now there's something I want to explain here, is that generally or normally there isn't only three forces acting here. There's actually six, because Newton's third law says for every action there's an equal but opposite reaction, which means if P is pulling this rod in that direction, then the wall is equally pulling back with the same magnitude that P is pulling. And because P is causing a tensile stress, also this P is also causing a tensile stress. This is actually Newton's third law. And in the same way, because these two forces are actually causing compressive stress in rod BC, then Newton's third law says the wall is also applying the same amount, which is 120 kilonewtons, 120 kilonewtons. So which means generally in this problem there were six forces that were acting on the beams. However, we considered only three forces. Why? Because these were reactional forces. We didn't really need to take them into consideration then, you see. Well, with time, as we go along these problems, it's going to be easy to actually understand that. So I just wanted to illustrate that there were actually more forces here, but we considered these three. So we considered the actual applied forces, and we didn't really consider the reaction forces. So yeah, this is actually the same principle here. We have two forces, one moving in that direction, but because they are balanced, we're actually going to take 1,200 newtons. Of course, in this figure, it doesn't really reflect some action up here, or it doesn't really appear like to be like your Newton's third law, but in principle, it's actually the same thing, because this object is stationary, and there's one force moving in that direction and another pulling in that direction and making sure that it's stable. So with that said, the force that is acting in the bone is actually 1,200. I hope that is clear, but I believe with time it's going to be much more easier for us to understand it. So with that said, we're going to be saying, therefore, the area at C is equal to our P, which is 1,200 newtons, all over our stress, which is 3.80 multiplied by 10, right? This is 10 to the Pascal. This is the kilopascal, the megapascals rather, and then I can put pascals here. And with that said, if you use your calculator, it gives you 0.00031,579 meters squared. This is simply because pascals is Newton per meter squared, and by mathematics, if Newton all over Newton per meter squared, the newtons will cancel and we'll be left with the meter squared. Now we have found a way of calculating the area. It's important that I explain the fact that the principle here we used, actually the first part is actually more strength of material, because it's an important principle. It was very much important to find to really know if you're gonna use 2 or 1, especially because in some instances you're gonna need 2 but the figure will be a different figure, you see. So we'll explain that as time goes by. Now that we are done with the SWK 210 strength of material principles, then we are left with the arithmetic. Now we can then go back to the sketch. Now that we know the cross-sectional area, we can simply say, remember the area at C, or the cross-sectional area at C, is equal to the area let me just say, is equal to the area as a result of the outside diameter minus the area as a result of the internal diameter, right? So now this is it. Now with that said, we know the area. We are basically saying the area here is actually the area as a result, the bigger cycle minus minus the smaller cycle. That's, I think, high school mathematics, so it shouldn't be that difficult. Now, with that said, as we continue, we then say, what is the area as a result of the, or what is the area of the bigger cycle, or the area as a result of the bigger, the outside diameter? And we know that it's pi over 4 multiplied by, what is the outside diameter? Or let me just say, outside diameter squared minus the same thing here is pi over 4 multiplied by the internal diameter squared, right? However, we know the area at C, the cross-sectional area, and we also know the diameter, which means here we only have one unknown, which is the D1. And therefore, if that be the case, then we can simply make a few rearrangements and just say, okay, we can just bring this one that side and bring that one that side and say, okay, let me take the longer route. So we know our AC is 0.000031579, right? Is equals to pi over 4 multiplied by our outside diameter is 25 millimeters. Now, if you convert it to meters for consistency, it's gonna be 0.02 meters, right, squared. Now minus our pi over 4 multiplied by our internal diameter squared. So with that said, you can simply make some rearrangement and make di the subject of the formula. So you can have our diameter, the internal diameter is equals to the square root of pi over 4 multiplied by 0.025 squared minus 0.000031579 all over pi over 4. So now therefore, our internal diameter, if you use your calculator, then becomes 0.000017521 meters. So this becomes our final answer. So yeah, it's very much important to understand that this problem is actually in two parts. The first part is your actual SWK concept or principle, which is using this equation here, and also importantly knowing how to apply the P. Actually, throughout this module is the tricky part is just gonna be knowing where actually is P, and not only P. Later, when other principles are actually introduced in the course, you'll also find yourself in a position where you're going to know how to use which of all these things that you are given. But with practice and with time, I'm very much convinced that it's going to be easy for anybody to do it if they really invest more time in it. Now, once you're done with that, then you're left with the second principle, which is something much more easy and straightforward, because it's something that I believe we all did in high school. So, well, thank you for your time, guys, and I hope to meet you again, guys, in the next video.